Now, let us have a look at the preparation of aldehydes and ketones. First, we look at the general methods of preparation for both aldehydes and ketones. So, we have already learned this either in previous chapters or in 11th standard. Aldehydes and ketones can be prepared by the oxidation of alcohols. Primary alcohols on oxidation will give aldehydes. So, an example would be ethanol, CH3, CH2OH. And here we need a very mild oxidizing agent, for example, pyridinium chlorochromate. And the product would be an aldehyde. If we are taking a secondary alcohol, for example, let us take propan-2-ol. Here we can use a stronger oxidizing agent like alkaline KMnO4, and the product would be a ketone. So oxidation of alcohols is an easy method for converting alcohols to aldehydes or ketones. Now, another method is again dehydrogenation. So here heated copper is the reagent. If we are using primary alcohol, say ethanol, it is treated with copper at 573 Kelvin, and again we get an aldehyde, ethanal. Whereas a secondary alcohol like butan-2-ol, on treating with copper at 573 Kelvin would give a ketone. Secondary alcohol would give a ketone. Another method is ozonolysis of alkenes. Let us do an example. Consider propene. The alkene is treated with ozone and we get a compound like this. The next method is called as ozonolysis. Let's do an example. Here the starting compound is an alkene. So let us start with propene. Propene is treated with ozone and the product is an ozonide. So both the pi bonds, both the carbon-carbon pi bonds are broken and the ozone molecule is literally adding into the middle of the two carbons. This compound is called as propene ozonide, or you can simply call it as an ozonide. This is an intermediate. Now, the ozonide is treated with zinc and water. So all the oxygen carbon bonds will break and reform, and you end up with two different compounds, CH3, CH double bond O, and on the other side, CH2 double bond O. So CH3CHO is ethanal. And what is CH2 double bond O? It is nothing but your methanol. Methanol. So CH2 double bond O can otherwise be written as HCHO and it is methanol. So ozonolysis of an alkene has led to two different products. So essentially what happened? You can easily identify the products without even doing the intermediate step. What actually happened was this double bond was broken and a double bond O was added here and another double bond O was added here. That will give you the products. But the intermediate again is very important. It is called as an ozonide. Let us do another example for ozonolysis. Let us consider a more substituted alkene. So for example, look at this one. So here this compound is called as 2-methyl bute-2-ene, right? This is a butene, bute-2-ene with a methyl substituent. Now this is treated with ozone. You will get an ozonide. The ozone adds in the middle, CH, CH3. This is the ozonide. This is then treated with zinc and water. And you end up with CH3, C double bond O CH3. So now you have a ketone. And on the other side, you have CH3, CH double bond O. So this has given you a ketone. This is propanone. Propanone, and this is ethanol. So if the alkene is substituted, then we will get a ketone through ozonolysis. Another method is the hydration of alkynes. Let us start with the simplest alkyne, that is ethyne. Ethyne is hydrated in the presence of mercuric sulfate and sulfuric acid, Hg2 plus ions and H plus ions. What first happens is an addition according to the Markovnikov rule. So here Markovnikov rule doesn't matter. So this becomes CH2 double bond CHOH. Water adds across the triple bond. The compound that you get here is called as an enol because it has an alcohol and it has a double bond. So it is called as an enol. Now the enol will undergo isomerization. The enol will undergo isomerization, and the product in this case will be an aldehyde, CH3 single bond CH double bond O. This is nothing but your ethanol. So ethyne on hydration will give ethanol, an aldehyde. As we learn more examples, we will see that only ethyne will give an aldehyde. Every other alkyne is going to give you a ketone because addition happens according to the Markovnikov rule. The oxygen will never go to the terminal carbon. It will always come to the middle carbon. So ethyne will give you ethanol, an aldehyde, but every other alkyne is going to give you a ketone. So let us look at another example. So let us consider propyne, CH3, C triple bond CH. Treated with water, mercuric ions and H plus ions. So when addition happens here, see this carbon has 2 hydrogens, this has no hydrogen. So the negative part of the addendum goes to carbon with less hydrogen. So OH will go to carbon with less hydrogen. So OH will go to the middle carbon. So your product would be CH3 COH double bond CH2. Again, this is an enol. The enol will undergo isomerization to give CH3 C double bond O CH3, which is propanone, which is a ketone. So except ethanol, all other alkynes will give ketone as the product. Now let us go to more specific methods of preparing aldehydes. A typical example is the Rosenmund reduction, where aldehyde is prepared from acyl chloride. So let us take benzoyl chloride as an example. So acyl chlorides are compounds where you have this particular group, C double bond OCl. Here the alkyl group, instead of the alkyl group, we have an aryl group. So it is called benzoyl chloride. So this is benzoyl chloride. It is treated with hydrogen in the presence of palladium and barium sulfate catalyst. And the chlorine is replaced by hydrogen and you end up getting benzaldehyde. This is Rosenmund reduction. Another method of preparing aldehydes is from nitriles. So nitriles are cyanides, C triple bond N. Compounds containing C triple bond N are called as nitriles. The first method is called Stephen reaction. The cyanide RCN, RC triple bond N is written as RCN, is treated with SnCl2, stannous chloride. Sn is thin, stannum, stannous chloride and HCl. Stannous chloride and HCl mixture is a reducing agent. It will reduce RC triple bond N to give RCH double bond NH. And on hydrolysis, RCH double bond NH will give you RCH double bond O. So basically the NH will go, and here instead of NH you will get oxygen. So RCH double bond O, which is your aldehyde. This is one method. Another method is to reduce the nitrile with a compound called as DiBALH. So what is DiBALH? Diisobutyl aluminium hydride. So let us see, aluminium is the central metal ion. Isobutyl. So what is isobutyl? This group, CH2, CH, CH3, CH3. So like this, one more. We know valency of aluminium is 3. So 2 of those valency will be taken up by isobutyl group and 1 valency will be taken up by hydrogen. So diisobutyl aluminium hydride. This is otherwise called as DiBALH. And DiBALH is a good reducing agent. So here DiBALH again will reduce RC triple bond N to RCH double bond NH, and that on hydrolysis the double bond NH will go and you will get RCH double bond O. So reduction with DiBALH will convert nitrile and further hydrolysis will convert the nitrile to aldehyde. So look at this example here. This is a double bonded compound containing the nitrile group, CN group. We can see that when it is reduced with DiBALH and hydrolyzed, we get an unsaturated aldehyde, which means DiBALH is very specific to the cyanide group. It does not touch the double bond. The double bond is not reduced. No hydrogen is added across the double bond. The double bond is retained as such. So, reduction with DiBALH will exclusively convert cyanide group to aldehyde group. That is another method. Similarly, esters can also be converted using DiBALH. Esters can also be converted to aldehyde. So here the OR dash part in the ester will be converted, will be substituted by hydrogen. So you will end up with an aldehyde. Another method for preparing aldehydes is from toluene and its derivatives. So what is toluene? Toluene is benzene ring with a CH3 group. So first let us look at the Ithard reaction. In the Ithard reaction, toluene is treated with chromyl chloride. So chromyl chloride looks something like this. Cr double bond O, Cl and Cl. This is the structure of chromyl chloride. Now what happens is, the hydrogen in CH3, 2 of those hydrogens get replaced by, so CH will remain instead of the two hydrogens, this part, so you can imagine it like this. So the actual mechanism is a little different. So you can imagine it like this. So let the two double bonds go and put an H here. Then what do you get? You get O, Cr, OH, Cl2, right? So O, Cr, OH, Cl2 twice. Two of the hydrogens will be replaced by O, Cr, OH, Cl2. So you get an intermediate which looks like this. The actual mechanism is a little more complicated, but for a simple understanding, you can consider it like this. Chromal chloride is CrO2Cl2. From that, you remove the double bonds, you put a hydrogen here and start with the O. So O, CrOH, Cl2. Two hydrogen atoms will be substituted. So you will end up with a chromium complex. That chromium complex on hydrolysis, all the large complex groups will be removed and it will be replaced by double bond O. So CH, double bond O, and you get benzaldehyde. This is the ETARD reaction. Another method is by treating it with CrO3, chromic oxide, in the presence of acetic anhydride. CH3CO twice O is acetic anhydride. So here again, the two hydrogens in CH3 will be replaced by OCOCH3 from this acetic anhydride. You will have OCOCH3. So two hydrogens will be replaced by OCOCH3. Again on hydrolysis, you will end up with benzaldehyde. Another method is by treating toluene with chlorine in the presence of UV light. So we know that substitution reaction will take place. The hydrogens will be replaced by chlorine. Either one hydrogen can be replaced or two or all three can be replaced. We use the compound where two hydrogens have been replaced with chlorines. This is called as benzyl chloride. And benzyl chloride again on hydrolysis will give you benzaldehyde. And finally, we have the Gattermann-Koch reaction where you take benzene, treat it with carbon monoxide and HCl in anhydrous aluminum chloride or copper chloride, and a CHO group is actually freshly introduced into the benzene ring and you get benzaldehyde. So this reaction actually is very important when you're doing conversions because it allows you to introduce a fresh carbon to a benzene ring. So now we have the preparations of ketones. Ketones can be prepared from acyl chlorides. So acyl chloride is RC double bond OCl. It is treated with dialkyl cadmium. So this compound here is called as dialkyl cadmium. You can see that there is a cadmium metal with two R groups. Okay, these are called organometallic compounds because there is a metal and there is also an organic part. So these are called organometallic compounds. So we take acyl chloride treated with dialkyl cadmium and we can see that the chlorine gets replaced by an R group. So like that, this happens for two molecules. So you get two molecules of R dash C double bond O R and the chlorines are taken up by cadmium. So the byproduct is cadmium chloride. So ketones can be prepared from acyl chlorides by treating with dialkyl cadmium. And how do you prepare dialkyl cadmium? You take a Grignard reagent, RMgX, you treat it with cadmium chloride and you will get dialkyl cadmium. So that is a side note actually, how to prepare dialkyl cadmium. Ketones can also be prepared from nitriles by treating them with Grignard reagent. So how does that work? So you take a nitrile RC triple bond N, you treat it with a Grignard reagent R-MgBr. So we know that this will split. The Grignard reagent will split into R- minus and MgBr plus. So the R- minus will come and attack this carbon because carbon is attached to a nitrogen. And obviously, nitrogen will have a small negative charge, carbon will have a positive charge because nitrogen is more electronegative. So the R minus group will come and attack the carbon and these electrons will shift here. So the next product would be RC double bond N minus. The R dash would be coming here and the MgBr plus would stay here. Hydrolyze this and this part would be removed and you will get a double bond O. Alright, the double bond N-MgBr would be replaced by double bond O and the product as a ketone. So let us look at an example, CH3, CH2, C triple bond N and C6H5MgBr. So the C6H5 will come and attack here and then this will go here. You will get the intermediate. On hydrolysis, that part will become double bond O. So the product, this is the intermediate, C double bond, N-MgBr, C6H5 has added here. And on hydrolysis, the double bond N-MgBr will be replaced by double bond O. And the product is what you would call propiophenol, or it is 1-phenyl propanone. 1-phenyl propanone. We have named this compound in the first video, 1-phenyl propanone. Ketones can also be prepared through Friedel-Crafts acylation. So we have learned this many times. Friedel-Crafts acylation, you take benzene ring, you treat it with an acyl halide. So CH3, C double bond OCl, for example. The catalyst is anhydrous aluminum chloride. Electrophilic substitution will happen. A hydrogen from benzene and the chlorine will be removed as HCl. And you will get C double bond OCH3 added onto the benzene ring. So here you can see C double bond O is attached to two other carbon atoms. So this is also a ketone. So Friedel-Crafts acylation is also used to prepare ketones. Now let's have a quick look at the physical properties of aldehydes and ketones. So generally, they have a melting point and boiling point that is higher than that of hydrocarbons and ethers because, of course, we saw they have dipole-dipole interaction. However, ketones do not have any hydrogen bonding. Aldehydes and ketones do not have any hydrogen bonding. So their melting point and boiling point will be less than that of alcohols. So generally, we have hydrocarbons which have the lowest MPPP, followed by ethers which are slightly polar, followed by aldehydes and ketones which have polarity but no hydrogen bonding, followed by alcohols which have a very high melting point and boiling point because of hydrogen bonding. This is about melting point and boiling point. Regarding solubility, lower members of aldehydes and ketones are soluble in water because they can form hydrogen bonds with water. Why? Carbonyl group, see, it is polar. It can form hydrogen bonds with water. It cannot form hydrogen bonds among its own molecules, but it can form hydrogen bonds with water molecules. So it is slightly soluble. But as the R group becomes larger, the lower members are soluble, but when you go to higher members, the alkyl group becomes larger and then the non-polar part is large. So the solubility decreases when you go to the larger members. Lower members of aldehydes and ketones have a pungent odor, but higher members do have a fragrant odor and they are sometimes used in perfumes and flavoring agents. So with that, we come to the end of this video where we have had a look at the preparation properties, physical properties, preparation and physical properties of aldehydes and ketones. Hope you've understood this. This would require a lot of practice from your end. You need to practice with examples. You need to do a lot of questions. Hope it goes well. Thank you.